All right, so in this video, we're going to briefly go over Introduction to Programming Concepts. And this is really a supplement to your reading Chapter 1 of the Python for Biomedical Informatics, the chapter entitled The Way of the Program, and working through its examples. And I'm going to skip over some of the material I have here and leave it as a written reference. First off, one thing to think of, what is the minimum you'll get out of this class? And I think that you may never be a programmer later in your life, but you're always, if you're in kind of this information related fields, biomedicine, you're going to be working with programmers. And I think the minimum you'll get out of this class is what a good program should look like, what the development process should be, and acknowledging that might evolve over time as different standards and practices get put into place. But we're going to skip over this story because I don't want it to be recorded, but maybe we'll talk about this in class. But it's important to know what a good programming product is, whether you're the one producing it or you're working with someone that's going to be producing it. So to really kind of understand programming, it's important to understand what is a computer. Here are some computers from Harvard, and if we look at the definition from the Oxford English Dictionary, the first definition now, a historical idea, is a computer is a person who makes calculations or computations. Now, its primary use is an electronic device for doing this kind of thing. What constitutes a computer? Well, we have hardware, operating system, we have some application we're running, and a user that's interacting with that application. And so it's important to keep in mind of what's the nature of the underlying hardware. The operating system is the operating system is going to be an intermediary between the applications that we write and the hardware itself. So programs do lots of different things. Within biomedical, text processing is a big thing. Within scientific computing, manipulation of numbers, etc., becomes a big thing. Essentially, computers do just about anything these days. We're going to skip over what a programming language is. That's well covered in the book. I have here a link to some histories of programming languages, what some of the influential languages that have been written over the years are. It's useful to kind of look at, see what you're familiar with. One thing that you might ask yourself, why are there so many languages? Fred Brooks, who was a famous, still alive, but a famous computer scientist from the 1950s onwards, said there's a lot of languages because people design languages so that they can get published. But more so, there's different problems require different solutions. And so languages exist for general use, but within that, they're usually kind of better for one particular aspect than, say, another programming languages. As new hardware is developed, there becomes new demands on the languages, and so new languages might arise from those demands. If we step back and think about, well, what is a program? At its most basic level, a program is a sequential list of instructions. And if we think about it in that sense, we write programs all the time. If you give someone driving instructions to your house, that is a kind of program. There's a famous example in computer science education of how to bake bread or how to make a peanut butter and jam sandwich that tries to illustrate the different restrictions of a computer programming language. But these set of instructions, sequential set of instructions that are followed, is really at the heart of what we're doing with writing computer programs. All or part of these might be things that are in our computer program. The program will get input, whether that's kind of hardwired into the code, which is what we'll start with, or it's reading it from a file, or it's asking a user to type something in. There's going to be some output, again, whether that's to a file or to the screen or to some other device. There's going to be some manipulation of the data, of numerics when we're doing some mathematical operations, for example. There's going to be some conditional execution. If my code, my data has such and such a value, then I'm going to do this. Otherwise, I'm going to do that. And finally, repetition. I'm going to do this over and over again until some criteria is met. And so you might think of this as like finding a repetition is like finding a parking spot where I will circle around the parking lot until I find a open parking spot. So that's the looping around the parking lot is a repetition. The conditional execution might be I'm going to look for a free parking spot while I have enough time, but if time gets short, then I will go and park at a pay lot. Kind of examples of concepts that will come up in our computer programs. So a programming language is defined by semantics and syntax. So semantics are the meaning that are assigned to various symbols, such as def, or while, or list, or the plus symbol. Whereas syntax are the rules used to connect the various symbols. So in Python, a equals 5 is syntactically correct, but 5 equals a is not. And so each language, most languages have kind of similarities in what kind of syntax they use in like, say, mathematical operations, but they will have varieties of different symbols that are defined for the language, and there will be variations in the syntax. So how do we go about creating a program? Well, the first thing we do is we analyze the problem. And this goes along with like the problem solving stuff that we'll work on. But first off, sit down and sketch out the problem. Don't even be sitting in front of a computer, perhaps. Just paper and pencil and ask, what is the problem? What is being asked of me? What data do I have? What do I need to manipulate? What should be my outcome? What should the program produce when it's finished? So thinking through the problem separate from the computer. Then you're going to outline how you're going to go about achieving that solution. So in programming, there's the concept of a pseudocode. So this is where, again, you're not writing in a program yet, but you're writing out more or less in English the specific steps that your computer program is going to take. And here you're getting into what's the structure of the program, what are the sequential list of instructions that are going to be done, what are the conditional executions, the questions we're going to ask, the ifs, the else, otherwise questions, and how will the data be represented? Am I going to be using numbers? Am I going to be using strings, etc.? Then we sit down and we write the program. So we pick the particular programming language we're going to use, Python, Java, C++, in this case Python. We write it out. It's not going to work correctly the first time, and so then we have to debug the program. We have to find the syntax and semantic errors where we're violating the rules of the language, and then we might have a perfectly valid Python language, but it doesn't do what we want it to do because our logic is incorrect. So those are the things that we're going to figure out in the debugging process. We're going to evaluate the program. Does it do what we want it to do? Is it nice and clean? And it won't be. And so if we have time or if we have motivation, then we'll go back and we'll start at step one and we'll refine the process and come up with a better computer program. So a lot of programming isn't, I wouldn't say it's necessarily hard, but it's not typically easy. So what makes programming hard? It kind of boils down to that computers are dumb and that computers are literal. They can only do exactly what you tell them to do. They can't infer meaning. And so that's where this peanut butter and jam sandwich example comes in of if you're giving someone instructions about how to make a peanut butter and jam sandwich, you may say, take 2 slices of bread from the loaf of bread. The person will infer that they need to open the loaf, take 2 slices of bread out, close the, put the tie back on the wrapping, and move on. But the computer can't add any of that contextual information. It can only do exactly what you tell it to do. So if you don't tell the computer to first open the bag that has the loaf of bread in it, the computer is going to be stuck. Keith Devlin, who's a math professor at Stanford, claims that computing is really about constructing, manipulating, and reasoning about abstraction. And then once you get a good handle on abstraction, then writing computer programs becomes more straightforward. And he has, how do we learn abstraction? Well, mathematics is a great example of an abstract topic of study. Art, jazz music, and computer programming. So I'm going to illustrate this with some things from Pablo Picasso. So here we have a bull. We all recognize this as a bull from the photograph, and there's lots of details with this bull. And here's a rendering of a bull from Pablo Picasso. We all would recognize this as a bull. It has the horns, snout, tail, its hoofs, etc. We don't have probably all the details in the Picasso drawing that we have in this bull, but we still have a lot. But here's another Picasso drawing of a bull where we've eliminated a lot of detail, but in this case, maybe with a little bit of imagination, we can still recognize this as being a bull. And so the key feature of abstraction is removing extraneous details. Of course, there's an art to this. It's not obvious what defines extraneous. When we're writing computer programs to model, to represent, say, a patient in a hospital, we have to limit what we can represent about that patient. We're probably not going to have eye color, how length of their hair, etc., as features that in some other context may be important and are certainly part of that person. But for the purpose of the abstraction of a person into a patient in our computer application of a medical record, these would be extraneous details. So there's some logical benefits to learning to program, that you learn systematic ways of thinking about data and relationships, et cetera, et cetera. And here's a link to an article that goes over the benefits of learning to program.